Welcome back. Today, we have a highly anticipated explainer lined up for you. We are taking a deep dive into Baidu's brand new ERNIE 5.1 model. Now, if you follow the AI space, you know perfectly well that right now everyone is just racing to build the biggest, smartest, most capable AI. But ERNIE 5.1, it's completely shaking things up. It's not just a step forward in capability, it is an absolute game changer in AI efficiency. This model is challenging the very way we think about training top-tier AI, and I am so excited to unpack exactly how they're doing this. Okay, let's dive into this. 6%. I just want you to hold that number in your head for a second. ERNIE 5.1 achieves its incredible frontier-level performance using only 6% of the pre-training cost of models at a similar scale. I mean, that is a jaw-dropping reduction. We aren't talking about some budget, lightweight model here. We are talking about a heavyweight contender built on absolute pennies compared to its rivals. So how is that even possible? Well, to answer that, here is our roadmap for today. We'll start with the frontier efficiency race, explore solving the seesaw problem, and look at a huge brain on a tiny budget. Then we'll hit code, math, and poetry before finally putting it to the test. Let's get right into it. All right, Section 1, the frontier efficiency race, moving beyond brute force scale. For a long time, the industry playbook was actually pretty simple. If you want a smarter AI, you just throw more money, more data, and way more compute power at it. It was literally a race of brute force scale, but we are officially moving beyond that era. ERNIE 5.1 completely abandons that brute force approach to take on massive, expensive models like GPT 5.5, DeepSeek V4 Pro, and Gemini 3.1 Pro. So instead of just outspending everyone, Baidu shifted their entire focus towards supreme efficiency, highly advanced reinforcement learning, and what's called expert capability fusion. It's all about working smarter, not harder. Moving to Section 2, solving the seesaw problem by merging specialist experts. Now, to understand why ERNIE 5.1's approach is so revolutionary, we first have to talk about one of the biggest architectural hurdles in modern AI development. It's called the seesaw problem. In traditional AI training, you have one massive, monolithic model trying to learn everything at once, but it inherently struggles to balance its skills. Say you tweak the model to make it an absolute expert at Python coding. Well, suddenly, its general reasoning skills might just plummet. It's exactly like a seesaw. One side goes up, the other comes crashing down. Being good at everything simultaneously has historically been a massive, massive headache. So, how exactly did they fix it? Baidu introduced an architecture called multi-stage on-policy distillation, or MOPD for short. Instead of training one giant model to do it all, they first train multiple independent expert models. One specifically for coding, one for reasoning, one for creativity. Step 2, they take all those distinct, highly specialized abilities and merge them into a single, unified student model. Finally, Step 3 uses online reinforcement learning to polish the whole thing up, ensuring conversational quality and alignment. The result here? The seesaw is perfectly balanced. It's a master of all trades, without any of the old compromises. Let's look at Section 3, huge brain, tiny budget, dramatic cost reductions. We've talked about the architectural theory with MOPD, but in practice, this translates to massive real-world financial dividends. Just take a look at these compression numbers. Thanks to this highly efficient expert merging architecture, ERNIE 5.1 compresses its total parameter size to just 1/3 of what is normally required for a model in this class. And the active parameters, the actual parts of the brain firing during a task, are cut in half. It is quite literally doing vastly more with significantly less. And here is where it matters most for users and developers, the price tag. When you look at a comparable frontier model, let's say GPT 5.5, you are looking at an input cost of about $5 per unit of tokens. But because ERNIE 5.1 is so architecturally efficient, its tier pricing comes in at an estimated 84 cents for the exact same input size. I mean, that is a staggering difference. You're getting frontier-level, bleeding-edge performance, but at a total fraction of the cost. Which brings us to Section 4, code, math, and poetry, validating the capabilities. Because, let's be real, sheep doesn't matter if it isn't actually good, right? We've seen the cost savings, now let's look at the raw performance metrics to see if it truly holds up against the heavyweights. And this brilliantly illustrates the sheer power of this model. On standard agentic workflow benchmarks, it is actively beating DeepSeek V4 Pro. In complex mathematical reasoning, it scored an incredible 99.6 on the notorious ERNIE 26 benchmark when using tool calls. For deep search QA, which means multi-hop retrieval and long context synthesis, it ranks in the top 4 globally. And perhaps most surprisingly, in creative writing, which is an area highly analytical models usually fail at, it is nearing the level of Gemini 3.1 Pro. It is competing directly with the absolute best closed-source models in the entire world. All right, finally, Section 5, putting it to the test with real-world prompts and puzzles. Benchmarks are great on paper, but we need to see how these models perform out in the wild. So we're going to pull some actual prompt tests straight from the source material. First up, a classic logic puzzle. The prompt asks, if 5 machines take 5 minutes to make 5 widgets, how long would 100 machines take to make 100 widgets? Now, this is a very common multi-step reasoning trap. Humans and basic AI alike naturally just want to jump to the number 100 here. But ERNIE 5.1 gets it right instantly. It takes 5 minutes. And what's really fascinating here is that the source shows ERNIE providing a detailed, perfectly logical breakdown of exactly why it takes 5 minutes, and doing it instantly, using its standard quick response tier. It didn't even need to be pushed into a delayed, deep thinking mode to solve it. Next, let's look at an hallucination test. The prompt was, who won the Nobel Prize in Physics in 2032? For a bit of context, the current date in the source material during this test was the year 2026. A weaker model might try to invent a sci-fi answer or just get totally confused. But ERNIE handles it flawlessly. It correctly identifies the current date, states clearly that the 2032 prize has not yet been awarded, and then logically concludes it will likely be revealed in October 2032. It easily passes the hallucination test by anchoring its vast knowledge base strictly to factual timeframes. No making things up. Let's dial up the difficulty a bit with a strict instruction following test. The prompt here is write exactly 12 words about space exploration, no punctuation. Now, this requires extreme precision. Any extra words or even dropping a single period at the end is a complete failure. Let's see what it did. Humans have long dreamed of exploring the vast stars and distant planets. Let's count them together. Humans, 1. Have, 2. Long, 3. Dreamed, 4. Of, 5. Exploring, 6. The, 7. Vast, 8. Stars, 9. And 10. Distant, 11. Planets, 12. Exactly 12 words, and absolutely no punctuation anywhere. A flawless execution of strict competing constraints. Now let's quickly pivot over to code to really test the MOPD architecture's debugging promises. Providing the model with a deliberately flawed piece of Python code, the prompt simply asks, what is wrong with this Python code snippet? Bam! It instantly identifies the precise error. It will raise an index error, list index out of range. This proves that despite its great general reasoning and language skills, its highly analytical, specialized coding capabilities remain completely robust and intact. So the crucial point we need to make here is the juxtaposition of strict, rigid logic and debugging capabilities placed directly against high-level creative writing. Remember the seesaw problem we talked about earlier? It's pretty easy for an AI to debug Python. It's easy for an AI to write a poem, but it is incredibly hard for an AI to be elite at both of those things at the exact same time. So let's see if its poetry actually holds up. The prompt asked for a sad 2-line poem about time. ERNIE 5.1 wrote, "The clock keeps ticking, stealing moments we can never reclaim. A second gone forever, leaving only shadows of our name." That is highly emotive, structurally sound poetry. And it's coming from the exact same brain that just accurately debugged a Python index error and solved a multi-step logic trap a minute ago. The seesaw problem hasn't just been mitigated, it truly seems to be solved here. Which leaves us with one final, incredibly provocative thought today. By successfully merging expert models, ERNIE 5.1 has achieved state-of-the-art capability across reasoning, coding, and creative writing, but it did so at just 1/3 the parameter size and a staggering 6% of the traditional pre-training cost. So I have to ask you, if a 6% budget utilizing smart architecture can match and even dethrone the giants of the industry, is the era of the massive, brute force, monolithic AI model officially over? It certainly looks like the future belongs to efficiency. Thank you so much for joining me on this explainer. I really hope you found it as fascinating as I did. Keep learning, and I'll see you next time.